Hi guys, I'm Alice and I'm a PhD student from UNSW. And today I'm going to be talking about how we can detect tidal features or more merging galaxies using a specific type of machine learning. So I'm sure most of you are familiar with the galaxy evolution model, but in the hierarchical merger model, larger, higher mass galaxies evolved through the merging of smaller, lower mass galaxies. And you can see in the video on the screen there that as these galaxies merge together, the immense gravitational forces between them pull out stellar material, which extends into space, forming what's known as tidal features. Here are some examples of galaxies with tidal features taken from the Hypersuprime Super Strategic Program. And by analyzing and characterizing these tidal features, we can understand more about the galaxy evolution process. To perform this kind of analysis, we need a large sample of galaxies with tidal features, which is hard to do for two reasons. First of all, they have extremely low surface brightnesses compared to astronomical imaging surveys like SDSS. And so that makes them hard to detect. And secondly, we lack automated classification mechanisms to assemble tidal feature samples, which means that they're mainly assembled through visual classification. Now that becomes a really big problem for large imaging surveys like LSST, which is going to run over the next 10 years and output billions of galaxy images, which I just don't want to visually classify. So this is where machine learning comes in. If you're not familiar with machine learning, we basically have two main classes. We've got supervised and unsupervised learning. Supervised learning uses labeled training data and learns to map inputs to corresponding outputs. It's really good for classification, like sorting objects according to shapes. Unsupervised learning, on the other hand, uses unlabeled training data and finds patterns within this input data. And it's good for clustering. So for example, grouping objects according to color. Now I'm looking for a tool that can perform classification. So unsupervised learning is not ideal, but supervised models usually need big training data sets that are labeled and that have to be rebuilt every time you want to use the model on data from a new survey. And that's just not really doable for tidal features. So that's why in this project, I'm using kind of a mix of these methods called self-supervised learning, which uses mostly unlabeled training data and can be used to find tidal features from a sample of thousands of uninteresting galaxies. The big advantage of self-supervised learning is that it can perform this sort of classification tasks with only a really small labeled data set, making it perfect for tidal feature detection. So getting into how the model actually works, we split up the model into two parts. We have the encoder, which uses unlabeled data, and then the classifier, which uses labeled data. So for the encoder, the input images are HSC images that are downloaded in 128 by 128 pixel cutouts, and they're downloaded in 5 bands, and we use about 45,000 of them for training. Before the images get encoded, they go through an augmentation process to create two different views of the same images. And the augmentations we apply include flipping the images, adding some noise to them, and randomly cropping them. Now, once the images are augmented, they go through the encoder, which encodes them into 128-dimensional representations. And we can label them view 1 and view 2 on the right here. And the model also has access to a queue of images, which are just drawn from a large data set of 45,000 images. Now, during training, the model will select an image from view 1, or a representation, and it'll look for a similar image in this queue of images. And we can call this the nearest neighbor of view 1. Then the model will take the view 2 version of the original image and calculate the loss between this view 2 version and the nearest neighbor of view 1. And the idea behind this is to train the model or to teach it that differently augmented versions of the same image should have similar representations. So we use a contrastive loss, which we force to be minimized when the view 2 version and the nearest neighbor of view 1 have similar representations. The next step in the model is the classifier, which is just a really simple model that takes in these encoded representations and outputs a number between 0 and 1, where for our model, 1 indicates a galaxy with tidal features and 0 a galaxy without tidal features. And this is the part of the model that uses labeled training data. So we have a data set of 300 galaxies with tidal features labeled 1 and 300 galaxies with no tidal features labeled 0. Now, getting into some results, here I have a plot of the mean area under a rock curve as a function of the number of labels used for training. I don't really have time to go into what a rock curve is, but all you need to know is that an ideal model has an area under the curve of 1, and a random model has an area under the curve of 0.5. So the higher the point is on this plot, the better the model is doing. And we plot this area for our self-supervised model that's in red, and then a supervised model in blue. And this supervised model was designed by Pearson et al. In 2019. So what we can see from this plot is, first of all, our model performs consistently better than the supervised model. And secondly, it maintains this performance even when we use very little training data. So when we use 600 labeled examples for training, we get an area under the curve of 0.91. But when we use only 50 examples for training, we still get an area under the curve of 0.89. Another really cool thing about self-supervised model is that you can perform this thing called a similarity search. So this uses just the encoder part of the model, not the classifier part. And what we do is we give the model an example image that we're interested in, called a query image on the left. And the model will look through the large data set of 45,000 images for similar images to this query image. So what I have here are the top 24 most similar images to the query image. So they're all assigned a similarity score, and I just have the top 24 with the highest similarity score here. And in red, I've outlined galaxies that I would visually classify as having tidal features. So this kind of tool, or similarity searches, are really useful when you want to find more examples of a specific type of object. What you can also do with self-supervised model is use this thing called uniform manifold approximation and projection, or UMAP. And this again just uses the encoded representation, takes them in and reduces them to, so these are 128 dimensional, and reduces them to a 2-dimensional projection that you can plot kind of on an XY grid. So what I've done is binned this projection space into cells and then selected one image from each cell to plot on its corresponding location in the projection space. And this really tells you how, like, what kind of information is contained in the representations and how they can be grouped together. So here what I notice is galaxies are grouped both according to their size in the cutout and their color. And we can also look at whether the scores assigned to the images by the classifier part of the model are related to their position in this UMAP projection plot. So I've just colored the UMAP plot according to the classifier score assigned, with red being scores close to 1, so tidal featured galaxies, and blue scores close to 0. And this really just tells me that the representations that we get from the encoder do have really meaningful information about tidal features, since they're all grouped together in this one space. So just to kind of summarize, I've used this type of machine learning called self-supervised learning to identify galaxies with tidal features. And this will be a really useful tool for going through really big surveys like LSST with minimal human input. And by using this kind of tool, I can assemble a large data set of galaxies with tidal features that I can start to analyze, look at their colors and shapes, and kind of draw conclusions about galaxy evolution. Thanks.